So do we still have the student volunteer here? Okay, that's fine. Yeah, I'm going to ask him to grab people back because of the coffee break. Okay, yeah, so our next talk is a very special event and honor that we are giving two Adversarial Machine Learning Rising Star Awards each year at the workshop. This is in honor of the great research impacts and also great research works done by young researchers. So the first awardee is Fatemehsadat Mireshghallah. So she's a fourth-year CSPhD candidate at the University of California, San Diego, advised by Taylor Kirkpatrick. She's also a research scientist at OpenMind. Her research interests are privacy-preserving machine learning, natural language processing, and fairness. So without ado, let's welcome Fatemeh for a wonderful talk.
Thank you. Thank you so much. Thanks for the introduction. Am I audible enough? Like if I stand here, people can still hear? Okay, because I tend to move around a lot when I talk. Okay, cool. So yeah, it's really nice to be here. Thank you for having me. And so I'm going to start my talk, but feel free to interrupt me and like ask questions. Like I really like it when things are interactive and it's not just me talking because I don't like hearing the sound of my own voice for too long. Okay. So yeah, I'm going to give kind of a summary of the research that I do, which is mostly on how much we can trust large language models and like what are the ethical and like safety, privacy issues that language models might have. So this would kind of be a bit more high level, I assume, compared to the talks that we had before, like in the workshop. So I hope that it's still like intriguing to the community. Cool. So, sorry. I went too far. Why is this? Neural models like recurrent neural networks, transformer models, which are like the kind of the most recent ones, and they're mostly like used right now. So we'll be focusing on them more. I'm not really going to go over the previous ones. And big transformer-based models. So transformers are an architecture. They're very dense, and they rely on this thing called attention, which we're not going to be like really using today. So I'm not going to like get into it. But what we really care about today is the different types of optimizations that you can have for transformer-based models. So you can have autoregressive language modeling, which is basically left to right, and we have non-autoregressive or masked language modeling. So in autoregressive, you condition each word on its left context. So like, what is the probability of the next word given the words I've seen so far? But in masked language modeling, what you try to optimize for is reconstructing the mask. So, given this, like the students open their books, if I mask open, what is the probability that my model would assign to open if it sees both the left and the right context? So that is masked language modeling, these are the top two like most common objectives in doing language modeling. Now, what are large language models? So this is just like kind of a phrase that the community uses to refer to transformer-based models because almost all of them are above 100 million parameters, so they're very large, and they go into billions. Like I assume you've seen like on Twitter or on like even press releases that like these large models are like doing this and that, and like are they becoming sentient and all those talks. So they're all large models because they have like millions and billions of parameters. And how they're deployed is that people use pre-train and fine-tune paradigm for deploying them. So what this means is that you first take these models, you pre-train them on huge, like a corpus that would be like 750 gigabytes, so like on a huge text corpus, which is scraped from the web. So they go over like all the text on the internet, and then they fine-tune these models with one of the objectives I mentioned, like either autoregressively or non-autoregressively, and then they get a pre-trained model. And then, for whatever task that you would have, you would fine-tune this pre-trained model. So the pre-trained model is kind of like a good initialization to then fine-tune on smaller domain-specific data sets. I normally use this cartoon to just like show what kind of things could go wrong, because it's like you have this bunch of linear, non-linear algebra, and you throw in like all the data in the universe, and you just like stare it until it gives you some good results on like a benchmark, which may or may not mean anything. So yeah, there are a lot of things that could go wrong when you're like doing this without really knowing what is happening, and you don't even know what kind of data you're feeding your model because it's just all scraped. Like no one has vetted it, no one has gone through it. So what could go wrong? Like what is good with these models? What is good is that they're performing better and better on benchmarks. They're good at generating text, It's very like, if you see the text, sometimes you don't even know if a human wrote it or not. And you're really good at like doing classifications, like all the benchmark tasks that we have. But one problem is that they're huge, which means they have high capacity for memorization. Like they're getting larger and larger. Like I haven't updated this graph in a while. Like there are way larger models right now as well. And then the training sets are also getting larger and larger. So whatever they are memorizing is things that we don't know what they are. And they could be harmful, hateful, they could be private. There are some recent papers that actually go through these like scraped data sets and find out like the type of harmful content that is in them. But mostly no one has ever cleaned these data sets. So there could be like, there could be anything there. So what gets memorized could be very, it could have a lot of issues. So in the rest of this talk, I'm going to first like really quickly go over the safety issues that could occur with large language models. Then we're going to go over how we can like measure leakage, which is like one issue with these models is the privacy leakage. So we're going to go over like how we can measure leakage, and finally we're going to talk about some open problems and future directions that we could be as a community could look at for working on. Okay, again, feel free to interrupt me at any point if you want to like ask a question or make any additions. So the first problem with large models is that they're leaky. And by leaky, what we mean is like what is shown in this cartoon is like, if you have a predictive model, you type in a prompt, it could fill in the prompt with some sentence that a user has written. So it could like literally regurgitate any data that it has seen. And for a while, people would use this cartoon, but there weren't any attacks that actually successfully did this. So everyone was like, well, it is possible theoretically, but no one has ever done it, so we don't know. But then in 2021, there was this attack that came out that they actually attacked GPT-2, which is a very commonly used large language model, and they actually extracted like full sequences from the model. So this is very much doable. And the reason I'm using Sesame Street cartoons here is that like language models, they often have Sesame Street character names, so it's kind of something that goes with large language models. Like you normally see, Bert and like other like Elmo and yeah. The second problem is that large models and even humans are sneaky. And by sneaky, what I mean is that we can, like by looking at some text, and also the models, they can guess some private attributes that might not have anything to do with the task that we're trying to do. So here, if you want to like do, you want to like guess people's professions based on like some pieces of text that they have written, the model can actually like figure out the gender of the person who has written it and get biased by it. So the gender boundary and the profession boundary, they are very close. So it's because the model can actually figure it out and get biased because of the bias that was also like in the data. So that is another problem. And the third problem that we call just being creepy, I'm going to show some examples to you that are generated, like we prompt dialogue GPT with this sentence. And these are the outputs that we get. I'm not going to read them. You can read them. So you can see like the bias in these two, and also the fact that they're just creepy. Like it's like weird. Why would the model say that? And you can try this with dialogue GPT yourself. Like there's an API. You won't get these sentences at the first run, but I didn't have to try so hard. I got like 20, 30 sentences, and it started getting creepy right there. So this is another thing that happens. And yeah, like why these things happen? Well, there is definitely some of these samples in the training data, but how can we prevent it? Like how do we want to control this? All of these are like questions that like people are working on, and we need to look at them more carefully. Okay, now let's focus on the leaky problem. How can we measure leakage in language models? So how do people just measure leakage in ML models in general? And what is leakage? Like how do we define leakage? So leakage is when you can infer something about the training data, any piece of information about the training data from a model that you wouldn't have been able to infer without that model. So it's something that you're learning from a model about training data. And one common way of measuring leakage is running membership inference attacks, which basically what they mean is that like if I give you data point X and I tell you, like, I ask you, is this part of the training data of a model, and I give you the model, you would be able to infer that. So, like, I give you X, I give you a model, and I ask you, is this part of the training data? And how membership inference attacks normally work is that, well, they feed that sample X to the model, they get the logits from X, and they also feed either training data or, like, non-member, like, test data that wasn't used in training, and in comparing these logits, they try to guess if a sample was in the training data or not. And the intuition is like normally if you have like just not even with the logits, if you only look at the loss, like if a sample was in the training set, it normally has lower loss compared to samples that are not in the training set. So that is kind of the intuition that like if the model has seen it, it behaves differently compared to a sample that it hasn't seen. And there are many membership inference attacks that like try to figure this out with different tricks. So one is shadow-based attacks where you train like 100 shadow models on different partitions of the data, and then using those you train other models that can basically look at the logits and tell you if something is a member or non-member. It doesn't like, we really don't need to like know exactly the details of shadow models, but what is important about them is that they are good, they are usually accurate, but they are inefficient, because you have to train 100 models on different partitions of the data and then train an attack model. And so it's like, it could be very intensive if you have like huge models, like in NLP that we have large language models. Now, in order to alleviate that, there's a second class of membership inference attacks. They're called population loss-based attacks, or in general, just like loss-based attacks that use thresholding. So how these work is that you basically, like if this is the histogram of the data and the dark salmon orange color is non-members, so it's a test set. You set a hard threshold based on how much false positive you want to get. So like here the red line is the threshold, and you also have a sample like the blue line, and you're asking your like attack, is this sample a training sample or not? And because it is to the right of the threshold, the model is going to be like, no, this is not a training sample because it has like high loss. So what is the problem here is that it's normally good because like a lot of the training samples like are to this side of the threshold, but then again, many of the training samples, especially difficult samples, are to the right. So if you have a sample that is in general a hard sample for any model to learn, you're going to always misclassify it like this because you're just looking at this hard threshold. So you're going to misclassify a lot of samples. So how can we get this to be more accurate? Like if you're only looking at the loss, like what can we do to be better? So the answer to that is people use references. So reference-based attacks normally train a bunch of reference models on data that is not exactly the training data, but data from the similar distribution. And what they do is that they use the reference to give them kind of a perspective. So it's like if a sample is hard and it has a high loss, like on my target model, it would also have a high loss on the reference model, but it would have an even higher loss. So now that I can look at the reference model, it's giving me perspective, so it helps me make the correct decision. So let me just like show you the mathematical notations. So instead of using the loss, I'm going to look at the likelihood ratio. I'm going to find the likelihood of the sample S under model R, which is the reference model. I'm going to find it under my main model, and then instead of thresholding on only the loss, I'm going to threshold on this ratio, and then make my decision, which means that I'm going to be more accurate now, because I'm like asking an expert or like a reference what they think. And if the reference is like, oh, this is a hard sample too, I can actually make a correct decision. Now this was like in general what people do with ML models. So how much of this like do we have in NLP? Like what have people done for large language models? In terms of extracting samples, measuring leakage, for autoregressive models, there is this metric that is commonly used called exposure metric. It tries to give you like a score of how easy it is to extract the sample from a model. So it's like a reconstruction kind of a metric. And then you also have this recent attack that I talked about at the beginning, which tries to extract samples from GPT-2. So how this attack works is that it's a mixture of an extraction attack and a membership attack. They first generate 500,000 samples from the model, and then they sift through them with a reference-based membership inference attack. And they show that like out of the 500,000, they guessed that 1,800. So it's like, just look at the ratio. It's like 500 to 1,800, 500,000 to 1,800. And then they have a 60% precision on that. So they generated 500,000 samples, but only 600 of them were really in the training set. Okay, so this was autoregressive models. Now, what do we have for masked language models, like the other class of models that I talked about, where we try to reconstruct a mask instead of like doing next word prediction? So how do these models work? I just want you to like remember that we are calculating the probability of mask given the rest of the sentence here. Not like autoregressive models. Okay, so people have tried to attack this class of models too, like right after the Carlini paper that did GPT-2 attack. People tried to do it for MLMs, and what happened was that they had no luck. Like they couldn't extract any samples, and they also had like very low, like a frequency-based baseline basically did better than attacks on MLMs. either membership inference or sample extraction. So people try to like prompt the model with like trying to guess people's diseases on a clinical model. They try to like fill in the blank. They try to probe the outputs, the logics, but nothing really worked. Like people couldn't get, good results, like accurate results out of it. So the attacks like had very low precision and recall basically. So so I said this. So what this kind of put the community in a state was that, okay, maybe MLMs are memorizing less than like autoregressive models. Maybe this kind of masking objective is actually better for privacy. It memorizes less, but autoregressive models memorize more because the attacks aren't really working. So is that the case, or do we just need a stronger attacks? Okay, if you want to do stronger attacks, what would we do? One type of a stronger attack, as we talked about, would be shadow models, which are kind of impossible here because, as I explained, like the pre-training phase takes days on like huge data. It's like you cannot train 100 of these models just to mount an attack. So that is like really not feasible, at least in an academic setup. But a better one would be reference-based attacks. They're more efficient, they're also accurate, so why not do that? But the problem is, with masked language models, you cannot get probability distributions over sentences. You get the probability of a mask, but you cannot factorize over it. So you cannot, like in a GPT model, you would just multiply the probability over each token, and you're going from left to right, so it's causal, and you can get a good probability distribution over a sentence. But with MLMs, there's no way of really getting a probability for a sentence. So what do we do here? So we need the probability of a sequence, but what we have is the conditional over like a mask token. So what we do here is like we propose something in our attack. It's like an energy-based formulation for the language model, which helps us actually calculate the likelihood ratio. So it's kind of like we're like, okay, we want to mount this attack, but we don't have all the tools. What can we do? Okay, let's change kind of the definition and the way we look at MLMs. We say that let's say we get a score from the masked language model. We don't care what the score is right now. We're going to call it an energy. So it's the E of S, which means like it's the energy of that sequence under this the target model. And we're going to define this. This is a softmax, right? Like it's e to the power of negative energy. And you also have Z, which is this. It's a normalization constant, and it's basically a summation over all possible sequences. So it's basically a summation of that the numerator, but over all possible sequences. So this would be a probability. It's just like softmax, and this would be the probability of the sequence. Now, if we want to calculate the likelihood ratio in this setup, what we would do is we would find this probability for the reference and for the target model, and we can just like write it out, do the logs, and basically what it ends up being is the negation of these two energy functions. So the whole trick, the main thing here, is that these normalization factors, they are actually constant, so we can just not care about them. And we can just let them be. They're not going to affect our attack because it's just a constant that would be the same for any sequence. So we can just leave it be there, and it's going to be like these two energy functions. And what these energy scores are, I'm going to really overly simplify it here, but if you're interested, like you can look at the paper. These energy functions are basically the loss of the model that you would get for masking a token. But the fact was that we wanted a score for the entire sequence, so we didn't want to like mask a single token. So what we do is we like take many samples, so we like randomly mask out different tokens in the sequence, and we average over the loss, and we use that as the energy. So that's what we do to get like a score, like a probability for a sequence under MLMs, which is like it's not normally easy to get. That's what we do. So how the attack would work is, you have your training data, you train a masked language model, so this would be your target model. In our case, we did clinical BERT, which means it was medical data, and you want to like guess the membership of a target sample, so you feed it to your target model, you get the energy, you feed it to a reference model, which we use PubMed BERT, which is another medical model, but it's not on the same training data, so it's like similar domain, but not the same data. We get the energy, and then what we do is we use that formulation from before to like guess if a sample is a member or not. So it's kind of like you're basically subtracting the losses of these two models for the given samples. And so for this example that I showed you that it would be hard to do it with the loss-based attack, if you use likelihood ratio, the two distributions completely they get shifted, and you can actually classify the harder samples easily. So now you have like a lower false positive, a lower false negative rate on your model, because like it's only a small portion of the training set that falls to the right of the threshold. Okay, so I'll go over some results real quickly here. Let's skip this. So normally in attack, like when we're looking at attacks and we want to measure their success, we look at the ROC curve, the area under the ROC curve, and the larger the area is, like the better the attack is. And you can see that like with the likelihood ratio attack, we have a higher AUC, but the baseline, only looking at the loss, has near random AUC. And if we zoom in on the low false positive rate area, which is like what people are mostly interested in, they want to be like very precise and accurate in like the samples that they say are members. So here we can see that actually like the gap is huge. So as you like increase the false positive ratio, the gap is smaller. But for lower false positive ratios, rates, you have a bigger gap, and it's actually better to use the reference model. The reference is really helpful. We also do another analysis, which was kind of like just a curiosity for us. And the question was, okay, what do the samples that are really memorized, what do they have in common? Like, can we guess, if I look at a sentence, can I guess if it's going to be memorized or not, if I'm training a model on it? And normally, like, the intuition is that the tails of the distribution get memorized. So we're like, okay, what does the tail of, like, kind of like medical notes, what would that be? So some of our guesses, we made some features, like, manually, was like maybe the number of digits, because usually like numbers are weird things. So maybe it's like numbers, maybe it's the sequence length, like longer sequences are bound to like get memorized more. These are just guesses. Maybe it's the number of non-alphanumeric tokens, because like, things like punctuations and stuff, those are weird, and like in medical like notations, they have some weird things. So maybe those get things memorized. And our last guess was like, what are the least frequent tokens in the sentence? So basically what this means is that like, are there any things that are very uncommon, like any words that are uncommon that are used in this sentence? So that is another feature, and we use these 4 features to guess membership of different samples. So it's like looking at these things, we try to train an MLP that would tell us if a sample is going to be memorized or not, and we have the precision here. So what we found was that it seems like the number of digits and the sequence length really don't matter in how much like the sequence has gotten memorized, but what really does matter is the number of non-alphanumeric tokens. So it's like if you have weird things in your sentence, it's going to like memorize more. And also, like if you have less frequent tokens, like tokens that are only like unigrams, bigrams, that only appear in the sentence, like those are also things that are bound to get memorized more. We also mix them, and we get like increased results. Okay, so far we saw that MLMs do actually memorize. We can have successful attacks. We just have to adjust our attacks. But MLMs, like the objective is a pre-training objective. These were all pre-trained models. How about fine-tuning? If I want to fine-tune a pre-trained model, then what happens? So are there any questions so far? Sorry, I went like at full speed. Okay. Okay, cool. Okay, so fine-tuning. We're running out of time, so I'm just going to go over this quickly. So fine-tuning is like when you take a pre-trained model, you want to adapt it to a domain. You have a data set that is smaller, and you try and fine-tune it for your given task. So one thing is that the fine-tuning task could be different from the pre-training task. Like you pre-trained with MLM, you fine-tune for classification. And also, again, since in fine-tuning we're doing domain adaptations, we argue that it could be more of a privacy concern, because like you might want to use this model for a company's like email completion system. So you fine-tune it on their emails. So this is more bound to be like a privacy concern compared to pre-training, where the data is like supposedly like public because it's like collected from the internet. So this is fine-tuning, and in NLP there are like different ways you can fine-tune a model. Just because these models are huge, people have come up with different efficient ways of fine-tuning them. So one baseline is if you fine-tune all parameters. This is what people normally like do in non-large models. You fine-tune your entire model. Again, because these models are large, the most common thing people do is they fine-tune heads. Heads are these attachable things to models. Like if you have a pre-trained model, if you want to do classification, you attach a classifier head based on the number of classes your task has. So you attach the head, you freeze the rest of the model, and you only fine-tune the head, which is basically, again, a classifier layer, nothing else. So you only fine-tune that. And then there's this other thing, which are called adapters, which are small modules people like spread in the network, and you only fine-tune them. And this is like 1% of the model parameters. So if you have a model that is like 124 million parameters, adapters would be 1 million added parameters. Head fine-tuning would be like 10 to 30 million parameters, and fine-tuning the entire model would be 124 million parameters. So we're going to look at these tree-based, but there are many other efficient, like prompt tuning and other ways that people like do things that no one has looked at. So like those are also things we could look into, like how those things memorize. Memorize more. Okay, so this is like a memorization graph during fine-tuning. So I'm going to walk you through it. It starts from here. The first phase is the fitting and is what we call fitting and memorization. So your perplexity is getting lower, validation perplexity, which lower is better, is kind of like loss. And your memorization is going higher. So you are learning, but you're also memorizing, which is, again, there are papers that say that sometimes learning and generalization does need some level of memorization. So this kind of makes sense so far. And then there is this phase, which is memorization only. So what is weird about this phase is that although the model is like memorizing heavily, it's not overfitting. The validation perplexity is not going higher. Like normally in domains where you don't do pre-training, or like at least in tasks that are not like this, what you see is like you see a complete curve. Like as soon as you hit a point where your model is optimized, you start going over and overfitting. Your validation goes up. But here you have this like full plateau where the model is like not overfitting, it's just memorizing. And then you have the last place where it's overfitting. So your validation is going down, your like full memorization is like, you definitely don't want to be there. So one like important finding that we had was that before this, people had found this plateau thing in fine-tuning and like other papers. But the thing was that it actually made people say, okay, we don't need early stopping, right? Because the model is not overfitting, the validation perplexity is not get worse. So it doesn't matter where we stop. Like let's train for as long as we want. But what you're saying is that if you really care about memorization and privacy, you really want to stop this early because you don't want to just memorize without getting really any benefits out of it. Although it's not overfitting, it doesn't mean it's not bad. Another trend that we find is, which was like, this was really surprising, was that like head fine tuning, which is this green teal dots here, is actually the worst. Like it has the worst like attack recall for worst perplexity. So although it doesn't have the most number of parameters, it's actually worse in terms of memorization. We have some guesses. Maybe it's because it's like at the end of the model, so it's like, it's where all the classification is happening, so it's memorizing more. But it was really surprising to us that this one memorized more than fine-tuning the entire model. Because like, again, a guess would be if a model is like larger, you have more parameters, it should memorize more. So it's a bit weird that head fine-tuning is the most memorizing one. But other than that, like full fine-tuning gives you better perplexity for more memorization. Adapters give you worse perplexity, but for way less memorization. So depending on where you want to be, you can like choose your method. And so this is that. And another interesting thing that we found, and it's not on this graph, is that we also repeated this experiment on a model that is trained from scratch. So it's not pre-trained. And what we found was that training on a model that is from scratch ends up like memorizing more. So it's interesting that like the fine-tuning kind of helps your model memorize less. It's kind of like it's giving you a good like starting point that already has a lot of samples. So maybe the model doesn't need to like memorize as many of your samples. So that was also something interesting that we found. Okay, so the last part. Open problems and future directions. So far, we saw some attacks. We saw some attacks on MLMs, that they're also susceptible to membership inference, but the one question we didn't answer is, like I mentioned, that maybe MLMs are memorizing less. The experiments that we ran and our attack doesn't really show that MLMs are memorizing more than GPT or like autoregressive models. So this is still an interesting question that like if you have the same setup with the same data sets and like similar models, if you have like an autoregressive model versus a masked language model, which one really memorizes more? Like we don't still really know the answer to this question. So this is one thing. Another thing is we haven't really been successful in extracting full training samples from MLMs. Again, maybe because of the way the masking works as opposed to like going word by word. You can't really extract samples, or maybe you just, again, need to adjust your attacks. So this is also really interesting, like how can we extract training samples from MLMs? And in general, even from GPT-2, where we could extract training samples, it was very inefficient, right? We extracted 500,000 samples in order to just get 600. So can we like change that? Can we come up with more efficient attacks? And finally, there are also some philosophical questions here too. Like if you really think about the stuff I was saying about leakage and everything, One thing is like, okay, we're measuring this leakage over a sample, but really, when I'm talking like in language, what do I want to preserve if I want to be private? Like, do I care about my single words? Do I care about a sentence? Or do I care about a document? Or like, what is the thing that gives away a secret in language when I'm talking? So there are also a lot of philosophical questions like going on about this that you can like think about. And we kind of did this fact like opinion paper on this too, which is like mostly philosophical, ethical questions that you could have. And finally, there are still many different like model architectures, like encoder decoders, many different optimizations that like in NLP that no one has really like tried to find the problems with, like what could go wrong there. People have mainly just focused on like autoregressive GPT-2, barely MLMs, and like let alone encoder decoder architectures. So these are also like some things that we as a community could look at. And that's it. Yeah, thank you for listening to my talk. And sorry, I think maybe I went over time a bit, but thank you.